Okay, so imagine this. What if you could build like a dream team of AI specialists, each one an expert, in their own field, all working together perfectly?
Right, instead of wrestling with these massive sort of try to do everything prompts.
Exactly. Imagine a structured setup where these smart AI agents actually collaborate,
Yeah.
passing tasks around efficiently, like a real top-notch team solving something complex.
That's exactly the exciting idea we're diving into today. We're going to unpack CrewAI. It's a really neat Python framework designed specifically to orchestrate these autonomous role-playing AI agents,
Mhm.
all working within clearly defined workflows. So, yeah, welcome to this deep dive.
And I'm really looking forward to digging into this with you. Our goal here is that by the end of our chat, you'll really get a handle on how these multi-agent systems, MES, as people often call them,
Right.
how systems powered by frameworks like CrewAI are fundamentally changing how we build AI solutions for business, taking them from just ideas all the way to robust production systems.
Yeah, absolutely. So at its core, CrewAI is an open source Python framework. It's built precisely for creating these collaborative AI agent crews.
Okay.
Now, if you've worked with LangChain, you can sort of think of CrewAI operating in a similar space,
Uh,
but it has a very specific focus, enabling these, let's say, complex multi-agent workflows where task delegation is explicitly tied to the defined role or expertise of each agent.
okay. So it's very structured in who does what.
Exactly. That kind of granular control lets you build these highly specialized AI units. Units you can then compose and, importantly, reuse. It moves away from the limitations of just having one big general purpose model trying to juggle everything.
Okay, that makes sense.
Yeah.
So let's break down one of these agents then. What are the key ingredients, the core elements that define an agent in CrewAI?
Sure. So each agent is defined by several key components. First up is its role.
Okay.
This specifies its area of expertise. Think of job titles like
Yes.
data analyst or maybe QA specialist.
Right.
Second, they have a specific goal. This needs to be a measurable objective they're aiming for, like, say, build an ETL pipeline or analyze customer feedback for sentiment.
Measurable.
Got it. Then there's the backstory. This is interesting. It provides context that shapes how the underlying language model, the LLM, behaves.
How so? Like personality?
Sort of, but more professional context. For example, a backstory might be a senior data engineer at a fintech company with 10 years of experience in complex data pipelines. It helps ground the AI's responses and actions in a specific context.
I see. It's like giving them a professional persona to guide their work.
Yeah.
What else is critical?
Absolutely. Next is the LLM binding. This specifies which language model the agent will actually use.
Okay.
And you've got flexibility here. It could be powerful ones like GPT-4 or Claude, or you could use local LLMs, maybe through something like Llama. That gives you options for cost, capability, privacy.
Right. Lots of choices there.
Definitely. And finally, agents are equipped with tools. These are integrations that let them interact with the outside world.
So they can actually do things.
Precisely. Things like a SQL tool to talk to databases, an HTTP client to fetch web data, or even tools to manage, say, Kubernetes clusters via an API.
Wow. Okay. So it's not just about having these separate AI minds. It's really about carefully defining their skills, their targets, their background story,
Yeah.
the language model powering them, and the specific instruments they can use. It feels very engineered.
That's a great way to put it. It is engineered. You're essentially defining these individual service units, the agents, along with their operating environment, the tools, the backstory. And critically, you also define the network, the topology of how they interact, the task sequencing, and how data flows between them.
Okay, so you have all these defined agents. How do they actually come together to, well, get stuff done? Give me the quick pitch.
Yeah.
How does CrewAI function at its core?
Okay. The elevator pitch. Think of it like this. CrewAI is kind of like Docker Compose, but for bringing up specialized AI services,
Okay.
combined with the workflow orchestration you might get from something like Prefect. But all specifically tailored for this world of collaborating AI agents. It lets you bring these specialized AI players online and get them working together smoothly as a team.
Okay, Docker Compose meets Prefect meets AI. I like that. Let's really dig into the machinery now. How does CrewAI actually instantiate these agents and coordinate them?
Right, let's get into the internals. The foundation is what you could call the agent factory. This is how individual agents get created, using the agent class in the framework.
Standard object creation.
Yes, but what's really powerful here is the ability to create custom agent classes by inheriting from that base agent class.
Subclassing. Okay, why is that useful?
Because it lets you encapsulate specific domain logic right inside the agent's definition. You make it a self-contained, reusable component tailored for a specific type of job.
Okay, can you give a concrete example? Like, how would that look in code, conceptually?
Sure. Let's imagine you need an agent specifically for handling ETL extract, transform, load processes.
Common task.
Very common. You could define a new class, say int agent, that inherits from CrewAI.agent. Inside this custom class, you might define its specific role, goal, backstory.
Like we discussed before?
Exactly. Role. Data engineer, goal. Build ETL pipeline, backstory. Senior data engineer at FinTech. You'd specify its tools, maybe a Squall tool, and a Python or APL tool for transformations. And you'd bind it to an LLM, perhaps OpenAI's GPT-4 Turbo.
Okay.
The key is you can also add custom methods to this ETL agent class. Maybe a method called processJob that contains the specific Python logic this agent uses when it gets an ETL task. It uses its tools, applies its logic.
Ah, so the business logic for that specific role is bundled right into the agent class itself.
Precisely. That encapsulation is huge. It keeps things organized, makes the agent highly reusable across different crews or projects. These custom agent classes become your expert building blocks.
That does sound powerful for building complex systems. So you've defined these specialized agents. How do you tell them how to collaborate on a bigger job?
That's where the task graph comes in. It's essentially a directed acyclic graph, a DAG.
Okay, like in data engineering workflows.
Exactly like that. Think of it as the blueprint for the project. It maps out all the individual task nodes your crew needs to tackle, showing the order they need to happen in and which tasks depend on others. Like a recipe, basically.
Right. Step one, then step two. How do you define those individual steps, those tasks, in the graph?
When you create a task object in CrewAI, you give it a few key things. A clear description, what actually needs to be done.
Extract sales data.
For example. Then you assign it to a specific agent, the one with the right role and tools for that job.
So assign the extract sales data task to our ETL agent.
Correct. And crucially, you define dependencies. Let's say you have textract for extracting data. You might then define a transform, also assigned to the ETL agent, but you explicitly state that transform depends on textract.
So CrewAI knows not to start the transform step until the extraction is successfully finished.
Exactly. It enforces that logical flow. You can also define an expected output schema for a task. This helps ensure the data passed between agents is in the format the next agent expects.
Like defining an API contract between agents.
That's a great analogy. And the beauty is, once you've laid out this graph, the tasks, agents, dependencies, schemas, CrewAI's engine takes over the scheduling and execution. It figures out what can run when based on the dependencies you set.
Okay, speaking of the engine.
Yeah.
That's the next piece, right?
Yeah.
The execution engine. What does that do?
Yes. The execution engine is the workhorse. It takes that task graph you defined and actually runs the tasks. It manages the scheduling, making sure dependencies are met.
Does it handle things like running tasks in parallel if possible?
It does. It respects concurrency limits you might set so you don't overload resources or APIs. And importantly, it has built-in mechanisms for resilience.
Like what? What if a task fails? An API times out.
Good question. It includes automatic retries, often with exponential backoff. So if a task fails, say calling an external API, it won't just give up immediately. It'll wait a bit, then try again. If it fails again, it waits longer before the next retry.
That's crucial for production systems. Builds in some fault tolerance.
Absolutely. You don't want a temporary network blip to derail an entire workflow.
Makes sense. What about keeping track of everything? Like, where is the workflow now? What's completed? If the system restarts, does it remember where it was?
That's handled by state persistence. For simple development or testing, you can just keep the workflow state in memory.
Okay, for demos maybe?
Right. But for real production deployments, CrewAI supports persisting the state to external systems like Redis or a PostgreSQL database.
Ah, so the workflow state survives restarts. Vital for long-running jobs.
Exactly. It knows which tasks are done, which are running, which are pending, even if the main process restarts.
Okay, and what about observing what's going on while it's running? Monitoring, logging?
That's where event hooks are incredibly useful. CrewAI lets you define functions that get triggered automatically when certain lifecycle events happen within the crew.
Like what sort of events?
Things like on-task start, on-task success, on-task fail, even on crew start or on crew end.
So you can hook into those moments.
Precisely. You can attach your own custom logic. For example, on task fail, you could log detailed error information to your monitoring system, maybe send an alert. On task success, you could record performance metrics like how long the task took.
That sounds like it gives you really good visibility for monitoring, debugging, and gathering performance data.
It does. It's key for understanding how your crew is performing and diagnosing issues.
And you mentioned earlier that agents use tools. How does that integration work under the hood? Is it easy to add new tools?
CrewAI provides a standardized tool API. This makes it straightforward for developers to build custom tools.
So you're not limited to just built-in tools.
Not at all. The framework provides the structure, but you can build tools to interact with pretty much anything you need: internal enterprise APIs, specific data lakes, cloud service controls, custom databases, you name it. As long as you wrap it in the tool API structure, an agent can be equipped with it.
Okay, that makes the system very extensible. So we have these agents, tasks, the engine, hooks, tools, all powerful pieces. How do people typically put these together? Are there common design patterns for structuring these multi-agent workflows in CrewAI?
Yes, definitely. Several common architecture patterns have emerged. The simplest is probably the pipeline pattern.
Like an assembly line.
Exactly. A linear sequence of tasks. Agent A does step 1, passes the result to Agent B for step 2, then Agent C for step 3. Think ETL, extract, transform, load, wellheap, report. Very straightforward.
Okay, makes sense for sequential processes. What else?
Another common one is the fan-out, fan-in pattern. Here, maybe one agent kicks off a task, but that task gets broken down and distributed to multiple specialist agents who work in parallel.
Like processing different parts of a document simultaneously.
Precisely. Or maybe enriching data points using different external APIs concurrently. Then another agent fans in it, collects all the results from the parallel workers, and aggregates them or synthesizes a final output. Great for speeding things up when tasks can be parallelized.
Efficient. Any other structures?
We also see hierarchical control. In this pattern, you might have a dedicated manager agent. Its main job isn't necessarily doing the core work, but rather assessing the situation and dynamically spawning or delegating subtasks to other worker agents.
So the workflow can adapt based on what's happening.
Exactly. It allows for more complex branching logic where the plan itself can evolve. And one more, the consensus council pattern.
Sounds intriguing.
Yeah, here you might have multiple agents, let's call them voting agents, all tackling the same problem independently. Maybe they each draft a response or a proposal. Then a central council agent looks at all these different outputs, compares them, maybe applies some criteria, and makes the final decision or synthesizes the best elements from each draft. It's useful for tasks requiring robustness or exploring multiple perspectives.
Wow, these patterns offer a lot of flexibility for different kinds of problems. Now, when you're actually building and deploying these systems, moving beyond just experimenting, what are the key best practices people should follow?
Right. Moving to production requires discipline. Several best practices are crucial. First, version control everything. Use Git not just for your code, but also for your agent definitions, their backstories, goals, tool configurations, even the LLM versions they're pinned to.
So you can reproduce results and roll back changes reliably.
Exactly. Reproducibility is key. Also, centralize your task schemas. If agents are passing data around, having clear version schemas for that data, maybe stored centrally, prevents misunderstandings and integration issues.
Good software engineering practice, basically. What about testing and deployment?
Absolutely integrate MAS workflows into your CI/CD pipelines. Write unit tests for your custom agent logic and tools. Write integration tests for entire crew workflows to ensure they behave as expected.
Okay.
And definitely containerize everything using Docker. Package your agents, their tools, the CrewAI engine itself into Docker images. This gives you consistent environments from development through testing to production.
Makes deployment much smoother. And security. Agents might need API keys or access to sensitive systems.
Security is paramount. Don't embed secrets in code or config files. Use a proper secrets management tool like HashiCorp Vault or your cloud provider's equivalent.
Right.
Agents or their tools retrieve secrets from the vault at runtime. And enforce role-based access control, or BAC, wherever possible, especially at the API level for the tools agents use. An agent should only have the minimum permissions needed to do its specific job.
Least privilege principle.
Yeah.
So it really boils down to applying solid software engineering and DevOps principles to these AI systems.
Precisely. And that analogy we used earlier holds up. Think about architecting these MAS workflows like you design a microservice ecosystem. Each agent is a service. Tasks are like the API contracts between them. Observability, automation, security, they're all just as critical.
Okay, let's make this super concrete. Can you walk us through a practical, maybe slightly simplified example? How could someone use CrewAI to automate a common business process?
Sure, let's take a classic example. Automated invoice processing. Many companies get tons of invoices as PDFs, and manually extracting data, validating it, getting approvals, processing payments, it's tedious and error-prone.
Definitely a common pain point. How would CrewAI tackle that?
Okay, first, we define the necessary agents, our crew members. We'd probably need an invoice receiver agent, its job, maybe monitor an S3 bucket using an S3 tool, and grab new invoice PDFs as they arrive.
Got it. Step 1, get the invoice.
Step 2, extract the text. We'd need an OC agent equipped with an OCR tool. Its goal is just to read the PDF and pull out the raw text.
Okay, text extracted, then what?
Validation. We'd have a validation agent. This one might use Python code, maybe some regular expressions or calls to an internal database via a tool to check if required fields are present, if the totals add up, if the vendor is valid, etc.
Checking against business rules.
Exactly. Now, what if validation fails? Or if the amount is over a certain threshold? We might need an approval agent. Its role is to route the flagged invoice, maybe create a task in a human workflow system for manual review and approval.
Handling exceptions and approval.
All right. And finally, assuming everything is validated and approved, if needed, we'd have a payment agent. This agent could use an HTTP client tool to securely interact with the payment processing API and trigger the actual payment.
Okay, so a whole team. Receiver, OCR reader, validator, approver, payer. Each specialized. How do you set this team up in CrewAI?
You'd instantiate each of these agent objects configured with their specific roles, goals, backstories, tools, and LLM bindings. Then you'd create a crew object, maybe name it Invoice Processing Crew, and pass it the list containing all these agent instances.
So the crew knows its members. Then you define the workflow using the task graph.
Precisely. You'd create the task objects. T1, receive invoice, assigned to invoice receiver agent. T2, OCR extract, assigned to OCR agent with T1 as a dependency.
Okay.
T3, validate fields, assigned to validation agent, depends on T2. T4, maybe request human approval if needed, assigned to approval agent, depending on the outcome of T3. And finally, T5, process payment, assigned to payment agent, depending on successful validation, T3, and potentially approval, T4.
So you're explicitly mapping out the entire flow and who's responsible for each step. Clear dependencies. How do you actually kick off the process for a new invoice?
Once the crew and the task graph are defined, it's typically very straightforward. You'd likely have some external trigger, like a new file appearing in S3. That trigger would invoke your CrewAI application. You'd use a method like crew.addTasks to add the defined task graph to the crew instance, and then simply call crew.run.
And CrewAI takes it from there, orchestrating the agents based on the graph.
Exactly. It manages the execution, passes the outputs of one task as inputs to the next, based on dependencies, handles retries, persistence, all of that.
And how would you monitor this? See if invoices are getting stuck or if the OCR is failing often.
That goes back to the event hooks and monitoring tools we discussed. You'd absolutely want to stream logs from all agents to a central system. You'd use hooks like on-task success and on-task fail to push metrics like processing time per invoice, OCR accuracy rates, validation failure reasons into Prometheus. Then you'd build Grafana dashboards to visualize all this in real time.
So you get a live view of the pipeline's health and performance.
Definitely. In a demo setup for something like this, you'd want to show off features like maybe the OCR fails and CrewAI automatically retries it a couple of times.
Right.
Or show how when the validation agent flags an issue, the workflow pauses, the approval agent fires off a notification, and the process waits for a human response before the payment agent can proceed. And all this is visible on those Grafana dashboards.
That sounds incredibly powerful. Building a complex, resilient, observable automation pipeline like that.
And the really striking thing is, the core CrewAI setup code to define that crew, those agents, and link those tasks together can often be surprisingly concise, maybe less than 20 lines of Python for the main orchestration part. It highlights how much heavy lifting the framework does for you.
That's impressive. In under 20 lines, you've built a production-grade, AI-driven invoice pipeline. Powerful statement. Okay, so you've prototyped this. It works great. Now, how do you take that invoice processing crew and make it truly production ready? Handle real volume, operate reliably 24/7.
Right. Scaling up involves serious operational considerations. Scaling, deployment, and operations become key. We already touched on containerization with Docker. That's step one, package agents and the engine to images.
Okay.
Step two is orchestration. For managing these containers at scale, Kubernetes is the standard choice for many. You'd likely use Helm charts to define and manage the deployment of your CrewAI application components onto the cluster.
So Kubernetes handles running the containers, restarting them if they fail, etc. What about handling varying load? Sometimes you have 10 invoices a minute, sometimes 1,000.
That's where auto-scaling comes in. Kubernetes has the horizontal pod auto-scaler, or HPA.
Wow.
You configure the HPA to monitor metrics like the length of the task queue waiting for a specific agent type, or maybe just CPU utilization of the agent pods. Based on thresholds you set, the HPA automatically increases or decreases the number of running instances, pods, for that agent type.
So it scales resources up and down with the workload. Smart.
Yeah.
And monitoring in production.
Even more critical in production, you need comprehensive monitoring. Again, Prometheus for scraping metrics, Grafana for visualization. You absolutely must instrument those CrewAI event hooks thoroughly to get deep insights into task timings, error rates, queue depths, everything.
Data is key. What about logs? With potentially hundreds of agent instances running.
You need centralized logging, sending all logs from all containers to a system like the ELK Snack, Elasticsearch, Logstash, Kibana, or Loki is essential. Otherwise, debugging is a nightmare.
Trying to find the right log file across dozens of pods?
Yeah.
Yeah, no thanks.
Exactly. And set up alerting. Configure alerts based on your logs and metrics, high error rates, queues backing up, tasks taking too long. Get notified immediately via Slack, PagerDuty, whatever your team uses when things go wrong.
Proactive awareness. Okay, infrastructure covered. What about the AI models themselves? LLMs get updated. How do you roll out a new model version safely?
Good point. Model versioning and rollout strategies are important. You don't want to just switch everyone to a new, untested LLM version overnight.
Might break things.
Could do. So strategies like blue-green deployments are useful. You deploy the new model version alongside the old one, shift a small amount of traffic, test, then gradually shift more. Or canary deployments, where you roll out the new model to just a small subset of agent instances first, monitor closely, and then expand if all looks good.
Gradual rollout, risk mitigation. Makes sense.
Yeah.
And cost. These LLM APIs aren't always cheap, especially at scale.
Cost control is a huge factor. You need strategies. Maybe throttling calls to the most expensive, highest capability models, use them only when strictly necessary. Perhaps use smaller, cheaper models for simpler tasks. Look for opportunities to batch requests to the LLM API if the provider supports it. Sometimes one call with multiple inputs is cheaper and faster than many individual calls.
Smart optimization. So running a big CrewAI deployment sounds a lot like running any complex distributed system.
It really is. That analogy of a microservice mesh for intelligent agents holds strong. Observability metrics, logs, traces, and automation for deployment, scaling, and recovery are absolutely your best friends when operating these systems in production.
This has been incredibly comprehensive. We've gone from the basic concepts all the way to production operations. I bet some listeners have specific questions bubbling up. Let's try and anticipate a couple. What about memory? How do you give these agents long-term memory so they learn or retain context beyond a single workflow run?
Great question. CrewAI itself is primarily focused on orchestrating the workflow execution, not built-in long-term memory persistence. However, it's designed to be extensible.
So you integrate it.
Exactly. You typically integrate with external memory solutions. For simpler key-value recall, maybe Redis. For more complex semantic memory, remembering the meaning of past interactions, you'd integrate a vector database like Pinecone, Weaviate, Chroma, etc.
How would the agent use that?
You'd build a custom tool for the agent. One tool to save memory, embedding the info and storing it in the vector DB, and another to recall memory, embedding a query and retrieving relevant past info. The agent uses these tools as part of its process.
So memory becomes another tool in their toolkit.
Okay.
Another common challenge.
That's good.
Securely handling API keys and other secrets for the tools those agents use. How do you manage that?
Yeah, absolutely critical. We touched on it, but to reiterate, never hard code secrets. Use a dedicated secrets management system like HashiCorp Vault, AWS Secrets Manager, Azure Key Vault, etc. The CrewAI application, or specifically the tool needing the secret, fetches it securely from the vault at runtime when it's needed. Don't store secrets in Git, config files, or environment variables if you can avoid it. Also, consider things like token rotation policies for API keys to minimize the window of exposure if a key ever were compromised.
Good security hygiene. Okay, one more potential issue, performance. If you have dozens or hundreds of agents all potentially hitting LLM APIs in parallel, how do you tune that? Avoid getting rate limited. Keep costs down.
Performance tuning with many parallel LLM calls is key. First, implement rate limiting on the client side within your CrewAI app or its tools so you don't accidentally flood the provider's API and get throttled or blocked.
Control the flow.
Right. Explore asynchronous execution of tasks where possible so one slow LLM call doesn't block other agents unnecessarily. Optimize your prompts, make them as concise as possible to reduce token count, which impacts cost and latency. And as mentioned, batching requests can sometimes help significantly if the LLM API supports it.
Makes sense. Optimize control batch. Got it. Any final quick hit tips for people building with CrewAI? Rapid fire optimization thoughts.
Okay, rapid fire. First, cache tool results aggressively where it makes sense. If an agent tool makes an API call or runs a query whose result doesn't change often, cache it. Saves time, saves API calls.
Good one.
Second, for tasks needing very consistent, predictable output, use more deterministic LLM settings. Lower the temperature parameter, for instance. Reduces randomness, makes testing and QA easier for those specific tasks.
Right.
Third, we mentioned batching API calls, but also think about aggregating work before calling an LLM if possible. Can one slightly more complex prompt achieve what you were planning to do with 3 separate prompts? That can save tokens and latency.
Consolidate requests. Excellent tips. This has been just a fantastic deep dive, really demystifying CrewAI and the world of multi-agent collaboration. Thank you so much for sharing all this insight.
It was my pleasure. It's genuinely exciting to see how quickly this field is moving and the kinds of sophisticated automation these frameworks are enabling.
And for all you listening, we really hope this exploration gave you a solid foundation in CrewAI and sparked some ideas about its potential. If you found this valuable, definitely check out the CrewAI project online. The documentation and community are great resources.
Yeah, definitely worth exploring.
And please, do join us again for our next deep dive into the technologies shaping our future.
Absolutely. Until next time.